Welcome back. We are now going to present many DFA algorithms, and all these will be illustrated not only through examples, but also through code. Okay, so let us look at some basic DFA operations one can perform. First, let us go through the code. So make partial DFA is a way to quickly make some DFA so that you can avoid specifying what is irrelevant. And all comments, all codes are commented. So if you ask for make P DFA's help function, help of make DFA P, it shows up. And also even Colab gives you completions for arguments. So basically it makes the DFA out of the quantities that you need to make. So you just pass in Q sigma delta Q naught F after parsing through markdown to machine. And it actually asserts whether is partially consistent. It actually checks for the alphabets with respect to the transitions and returns a new DFA. The make DFA function is essentially, again, a helper inside. It actually makes a DFA which is assumed to be completely specified. And it is administering another consistency check is consistent DFA. You can look at all these consistency checks. Totalized DFA is typically applied after make partial. And what it is checking is you are given a partially consistent DFA. And then it is checking whether you need to totalize. So is it the case that all the transitions have been accounted for? So it's already total, then return it. Otherwise, you make a copy of the incoming delta and find the gaps in the transition relation. And black hole absorbent moves are introduced. So all the unmentioned moves are made to go to the absorbent state, which is the black hole, and update the incoming deltas and finish up with returning the finished delta. So with all this, the markdown to machine is a parser that takes in the specifications, parses it, and calls these helpers. We'll be studying markdown to machine in context-free parsing. So if you actually make one of these DFA at this point, and assuming that these have been loaded, I think it has been. If not, we'll give it a whack. So these have been loaded. And so then you can actually look at DFA B0, which is this one, begin 0. And you can extract pieces of the DFA like this. And now you can make a DFA with, let's view this, begin 0. It begins with a 0. A DFA that ends with a 1 can be made. And then you can, of course, do a Boolean operations, union, intersection, complementation. Stepping of a DFA is basically going to allow you to step the DFA through a symbol, runs it over a string, which recursively steps. Accepts is a test that checks whether the final state contains the current ending state of the run. And now you can check whether DFA ends in 1, accepts something. And now you can do begin 0 and end 1 intersection, and you get this machine, begin 0 and end with 1. And when you do that, you actually see the product state as the state name. So the product construction is done inside. And you can also do DFA begin 0 or end 1 and see its diagram, which has now the complement of the states, I guess. So this is the begin 0 and end 1. So this is begin 0 or, so it is a superset of the states. And now you can try to minimize and see whether some things can be eliminated. So begin 0 or end 1 is subject to minimization, in which case this FI state, which now is the final state that you cannot leave, even if you go to FF. You can merge these two states. So FI, the state FI becomes the representative of FF. Complementation is simply done by taking the original components of the DFA and subtracting the current final states from the totality of the states. That's all. And so that way you are flipping the finals and non-finals. And the delta is simply returned the same way. You, of course, totalize it at this point. Now you can complement the begin 0 or N1 and see what it is. And it actually moves the acceptance state to this one. So instead of these 3 states, you get these 2 states as the final. Now you can complement B0 or complement N1 can be complemented, and it should result in the AND behavior, like De Morgan that we saw. The code for union is simple, except we make sure that the DFAs are consistent. Also, we check whether the alphabets agree. If not, we are going to make the alphabets the union of the alphabets of the incoming machine, and then basically do the Cartesian product of the states of the machine. And the final states are products of the starting states, and if one of the DFA accepts. So final of one, Cartesian with states of the other, or the other way. The machine basically marches on lockstep. So starting state is the start of the both. And the delta function is introduced in a declarative way. You can actually see that if Q1 goes to Q1 prime, Q2 goes to Q2 prime, you allow for the first machine to march according to its delta, the second machine according to its delta. And that will be the component of delta for the original machine, the full machine. Then you had to prune unreach. This is a step that gets interesting, because when you do union intersection, sometimes you get disconnected islands of states that cannot be reached, and it's distracting. So this actually prunes all those unconnected but self-contained islands of states that cannot be reached. Similarly for intersection, except we try to respect the joint move. So the basically difference can be that you basically march according to both. And here you basically, of course, the states are always Cartesian products. The final state is if one of them accepts. And here, if the final is, if both the finals are in the Cartesian product for the final of the intersection. Eliminating unreachable states is a very simple walk, breadth first walk, that actually goes through the set of reachable states and makes a DFA out of what remains. The isomorphism test is pretty easy. It checks whether the machines are consistent. Then it says if the lengths of the states, meaning the number of states, are the same, then isomorphism boils down to language equivalence. Language equivalence is a recursive traversal from the start states. You march the machines till you can exhibit the status of a pair of states being reached in an opposite sense. So if one machine reaches a final, the other doesn't, the machines are not the same. At that point, you recurse back, providing a false. If you cannot exhibit the same and you exhaust all the states, then the machines are the same, language-wise. Same status is checking whether the finality status is the same. And there's a helper function that uses a lambda and filter, which makes the writing of the code much easier. DFA minimization is a dynamic programming-based algorithm that is widely taught. And the mathematical description is given here. And how you fill in the configurations of the machines is also mentioned here. And basically, these dots represent the n-choose 2 pairs of states that need to be compared for whether they can be distinguished or not. So initially, so A and IF are getting compared in this place where this dot is mentioned. And you begin the machine with a frame containing all -1 or dot. You can use either. And all the finals and non-finals are zero distinguishable, meaning they have been distinguished already by an epsilon test. No character needs to be administered. Then you see whether you can find a distinction between two states that can be reached from indistinguishable as yet states. There is an actual chatty option that will tell you how the minimization is actually working, so you don't need to worry about understanding it at this point. Let us see the printout of the chatty option. If two frames repeat, then the surviving minus ones are points at which those states have not been distinguished. And then you had to form equivalence classes of states and present the results. So this English commentary tells you how the minimization typically works. And this is a fixed point function that actually is the heart. So you basically say changed equal to true while changed equal to false. And you compare the marches of the machines and see if you can distinguish the next states. And this is quite readable. I will encourage you to read and find how the distinguished pair is established, and there's a printout coming. So when you get the printouts in the chatty option, you can also examine how the printouts were generated. And you can print the dynamic programming table at each point. And the minimization algorithm itself calls these helpers by separating the finals and non-finals, and calls the fixed point function. And then once the machine is obtained, the minimized machine, you form representatives of equivalence classes. And then you form the actual machine. And then also you make sure that the minimized machine doesn't have humongous state names that fill a whole page. So there's an option to keep the state names compressed according to the user specification. So all these utilities are packaged in here. And so this entire machine, the description can be run. And so we can actually run time and run all. I don't know whether this is ready to run. Let us give it a whack. So this is books figure 7. And now minimize with chatty equal to true and state name equal to verbose. So in the chatty option, you can actually get the printout of the dynamic programming table. The final programming table is shown, but initially it shows how the final and non-final are zero distinguished, thus resulting in all these zeros in the otherwise dot or undetermined dynamic programming status. And then seeing if FS6 and FS3 can be distinguished by any symbol. This is how the tests are done. So if you actually look at the machine now, so at this point, this is the machine that we are minimizing. And now you can see what we are trying to distinguish, essentially seeing if FS6 and FS3 can be distinguished. FS6 and FS3 can indeed be distinguished. If you step one symbol from here, you are in a non-final, and one step from here, you are in a final. And found a distinguishing pair through 0, and marking FS6 and FS3 as one distinguishable. This is how the table filling works. Hence, we must sweep the algorithm once more. So this entire running commentary is how the states are merged or indicated to be distinguished, actually, not merged yet. And you can walk through this with respect to any machine. And now collecting the equivalence classes and see whether there is any overlap between the equivalence classes. And at that point, the minimized machine can be printed. And if you want to, state name max size controls the size of the merged states, because you don't want them to be too large. And if you use the edges, you get a clean looking machine like that, which is the minimized version corresponding to this machine. So you get an idea of how the machine minimization works. And there's a much better or cleaner or simpler algorithm called Brzezowski's minimization that we will be showing. So which actually can be done if a reverse DFA is defined. Yeah, it is defined. And NFA to DFA is defined. And so since these are defined, why don't we give that algorithm a go? So Brzezowski's algorithm is nothing but reverse determinize, reverse determinize. That's it. And the algorithm can be stopped as reverse determinize if the language is reversal closed. If not, you have to do it again. Because what Brzezowski proves is that given any DFA whose language is reversal closed, its minimal form is reverse determinants. So you get the minimal DFA of the reverse of the language of the given DFA. So if it's reversal closed, you can stop here. But if the language is not reversal closed, then you have to do the step once again. So let us test it out. And the machine that we just now minimized has a, let's do Blimp. Blimp is a machine that has not been done yet. So this is the Blimp. So let us look at the Blimp and apply minimization in both ways. So Blimp dot object DFA of Blimp. Let's not bother to fuse the edges. It is a machine like that. So min Blimp equal to min DFA of Blimp. We don't want the chatty option. And the dot object DFA min Blimp can be seen. And the Blimp machine minimizes to this one. Now do the Brzezowski min Blimp equal to min. So reverse determinize, NFA to DFA, row DFA, NFA to DFA, row DFA of Blimp. That's it. And now you can say dot object DFA G Brzezowski min Blimp like that. At this point, you get identical machine. So now you can actually see whether you can do just the first part. Even is this reversal closed? I don't know. So if the D Blimp is the D Blimp machine is reversal closed, this should have been sufficient. Let me call it questionable. And it is questionable at this point. And let us see what happens. So if I run this one, you get something, and you get this machine. And now, is this the same as the other machine that we got, a min Blimp? And so apparently the machines look reversal closed, although this is not a proof. So again, for the original machine that you can actually try, this is the machine. So min book figure 57. So let us do a one-liner. So dot object DFA NFA to DFA. This has not been introduced yet. NFA to DFA row reverse DFA of book figure 67 would actually draw the machine. And indeed, the Blimp was actually a bloated version of this machine. But this machine also minimizes. So now you can see how Brzezowski's algorithm makes minimization a real sweet deal. The proof of why Brzezowski's algorithm works is beyond this lecture. You can read Brzezowski's paper. Basically, what happens is if there are two transitions on the same symbol coming to a state, then that becomes a non-deterministic situation going backwards after the reversal. And then when you have, so two A's coming in to one state will become that state leading through two A's to two different states. And now, so that's a non-determinism on A. If you minimize it, the initial states, starting states get collapsed. So it actually collapses the machine backwards. And then the flows are reversed. So the initial minimal form is the minimal form of the machine flowing backwards. And then when you allow it enough time, meaning do one more, it'll become the minimization. So Professor John Brzezinski has given me a lot of advice. And when he was alive, unfortunately passed away several years ago. When he was alive, he actually went through my course and my software, and we had some nice Skype calls. And he told me that in some cases, his algorithm produces minimal forms much more quickly, although the minimal forms are supposed to be identical. So we don't doubt it. Let us see whether we have RE to NFA defined. It's not defined here. So let's make an arbitrary DFA, which can be minimized, and you can check whether the machines are isomorphic at the end of the day. So the isomorphism test will pass, and you can easily check it out that this indeed carries out the minimization. So this actually was a quick tour through the code for several of the constructions, and also I illustrated the minimization algorithm in a chatty mode, and also gave you Brzezinski's minimization. So I hope this was interesting, and this actually helps accelerate many of the things that instructors normally trudge through in teaching this material. Having this material in their fingertips makes students quite adapted to understanding what is going on. So I will end this recording now, and see you next time.